Now, to understand that, heuristically, when I estimate the coefficients in a regression, what I do is I say, gee, I have this weird thing called the likelihood, which is just the probability you would observe the data that you've got given this choice of coefficients. And then you vary the coefficients around, well, the computer does, varies those coefficients around and finds the one that makes that probability the highest. That probability is the likelihood. You want to maximize it by choosing the best betas. Okay? So remember that the expected value of y is a function of the betas. And in particular, for linear regression, we solve for beta by minimizing the sum of the squared errors, which is the observed minus the expected is the error, and the expected depends on beta because it's beta 0 plus beta 1x. Well, how do you maximize a function? Well, you hire a computer programmer who knows numerical analysis and they write a program. So a statistician named Wedderburn took a close look at those programs. And what he showed was these programs iterate around and try to get closer and closer and closer. And while they're doing that, the only thing that they make use of is what g of mu is. Is it a log link, a logit link, an identity link, and what are the x's, right? And how v, the variance, depends on mu. And he said, well, that's very interesting. I don't need to know really what the probability distribution of the data is, because this program, which maximizes that probability, right, doesn't actually use it. It uses this, and it uses that, and it produces valid estimates. So what if I tried this for data that didn't quite fit the probability distribution I thought? And he showed that he can still get valid estimates provided you correctly specify what g and v are. And this is called quasi-likelihood. So let me give you examples of generalized linear models. There's normally distributed outcome data. The range of y in principle goes from minus infinity to infinity. If our outcome is blood pressure, we think the negative values are probably not going to happen, but right? For binary data, it's 0, 1. For Poisson data, it's counts. Gamma is another nice distribution, and that has y's that range from 0 to infinity, which may make more sense for a lot of continuous outcomes that we measure, which can't really be negative. You know, your hemoglobin count, for example, right? Okay, and then the expected value of y is mu, and then there's a link function like the identity link, the logit, the log, and a variance function for these different things. And for quasi-likelihood, you get to pick what the appropriate link and variance function is. So, and you can mix and match them from things that are more normally used for different distributions. Now that sounds pretty confusing, so let me give you some examples. Let's say I'm looking at blood pressure. Nice continuous variable. Suppose I discover that as blood pressure goes up, the variance is not constant. It goes up also. So in fact, instead of being independent of the expected value, like normally distributed data, it in fact increases with the expected value. So this isn't really normally distributed data, even though it looks kind of normal, right? What could I do? Well, I could say the link is the identity link. I'm still going to fit a linear regression. Blood pressure is B0 plus B1 times age plus B2 times gender, etc. But I'm going to tell the computer that actually the variance increases with the expected value. And then I tell my generalized linear model program to fit that. Now, do I need to do this? Is this a realistic example? This is a plot of systolic blood pressure versus age in the first National Health and Nutrition Examination Survey in the US, and you can see that the range of variation at lower ages and lower blood pressures is considerably less than the range of variation at higher ages when blood pressure is higher. In fact, the variance of blood pressure increases with the expected value, and now we have a way to fit our model that says, okay, that assumption was net, no problem. I say that the variance is equal to mu, and I go do my regression, and I've taken care of it. Instead of making the wrong assumption about the variance, I can make the right assumption, get my coefficients, and valid confidence intervals. Hair mercury levels in women during pregnancy are predictors of cognitive function in their children when they grow up. The distribution of hair mercury levels is not normal. It's skewed because some people eat a lot more fish than other people, and that's pretty much where we get it. Now, a typical thing that people do to solve that is say, well, I'll take the log of hair mercury, and now let me regress the log of hair mercury against fish intake and various other things. But if I do that, I'm specifying a nonlinear multiplicative model for all my outcome related to all the predictors, right? Because if the log of y is that, then if I exponentiate both sides, I get this, and then, e to the blah plus shtick is e to the blah times e to the shtick, and so this turns into that, and the effect of x2 is multiplicative on the effect of x1. Maybe I don't think that's true. Why should the effect of eating a lot of tuna fish, for example, be multiplicative on the effect of eating, say, some other kind of fish or some other source of mercury? So instead, I could specify an identity link which says, no, I'm going to do a linear additive regression. I'm going to say that the expected value of y is b1 x1 plus b2 x2, etc., but that the distribution of the data is skewed. For example, the gamma distribution. All of these curves are examples of the gamma distribution for different parameter choices of that distribution. So as you see, it can look exponential. It can look normal, like that yellow one, and it can be various forms of skewed distributions, like the green or the light blue or the dark blue, depending on the parameters of the distribution. It has two parameters. So if your distribution is pretty normal, no problem, you can fit that. If it's really skewed, you can fit that. If it's a little skewed, you can fit that. So this is a way to deal with having skewed data without having to fit a multiplicative model. Count data we generally model with a Poisson regression. But the Poisson regression assumes that the variance is equal to the expected value. Exactly equal. There's only one parameter in the Poisson distribution. And so that's it. So that means that conditional on the predictors, if everyone's risk is the same, then that ought to happen. But that means you have to have all of the predictors in your model. If you don't have all the predictors in your model, and they're not confounders, you say to yourself, who cares? But if you don't have all of them, then there's some unexplained variation going on, which is going to make the variance bigger than the expected value, than mu. And so this is very likely to occur. And so quasi-likelihood comes in, and you can say, okay, maybe the variance is 1.2 times the expected value. I still think that omitted variable is not a confounder, but I admit that because I don't have it, my variance is too big, and therefore I'm going to underestimate the confidence intervals for my variables. I might conclude something is significant when it's not. I will fix that up by saying that. Okay? In SAS, that's called the scale parameter. And so again, in any generalized linear model, there's a standard way to specify this. And this is called an over-dispersed Poisson distribution. Now, a Poisson distribution that's a little too fat around the middle, which is a problem some of us have, isn't really Poisson distributed. In fact, I can't write down what that distribution looks like, but I don't need to. All I need to do is say that, and I'm good to go. So I hope that I've explained to you, one, that all regression analyses are almost identical. They're a pretty happy family, that they differ in what their link function, the function of the expected value, is for regressing that kind of outcome, and in their variance function, that we can analyze them all as part of a happy family package, and that package allows us to deal with situations where the data doesn't really have the distribution that standardly we've assumed it did, and still get valid inferences. Thank you.